Hello everyone, welcome to my next tutorial. It is a fifth part of the solar cell application simulation. In this tutorial, we will be discuss how we can calculate maximum short circuit current function with the active layer thickness and CT excitant parameters. So before start of my tutorial, I want to introduce myself. I am Sahil Verma, application engineer of the well-known company Impulse Technology. About the company Pulse Technology, their services and partnership with other companies we have already discussed in my previous video. Who has not seen it, please check out the playlist. Firstly, we will be discussing a small PPT about the optical modeling in organic solar cells and what we are going to simulate in here. Then we will proceed towards the Setfos tools and perform our tutorial related to this. We are going to simulate in here optical modeling in organic solar cells, fully coupled organic photovoltaic simulations, and optical absorption. In optical modeling in organic solar cells, at here we considering one of the researcher, Hope, which investigated the maximum short circuit current as a function of the active layer thickness as well as investigated the absorbed fraction of light. So the similar tutorial we will perform in a Setfos. The second one is fully coupled organic photovoltaic simulation. This tutorial based on Hagerman that author published a sensitive analysis of CT state excitant in organic photovoltaic solar cell. I will be help you how we can find these excitant parameters in the Setfos tools. Third is optical absorption. The maximum achievable photocurrent can be calculated by integrating over the number of photons which are absorbed in the active layer. So these property we will be calculates in the Setfos tools, and I will be tell you how we can calculate these parameters. So let's move on the Setfos tool. Click at here the right side and run as an administrator. About the Setfos, we have already discussed in my previous video. So who has not seen it, please check out the playlist so you can get a lot of the information about the Setfos tools, how we can put inputs, number of the modules present in the Setfos tool, we can get a lot of the information. It is the new dropping models which are introduced in the Setfos tools. I have already spoken about the previous video, like my first and second video. You can see it is a new Setfos version which are available and the new features which will be introduced in the Setfos tool. So before start of my tutorial, I will provide the brief explanation of Setfos GUI. So it is the Setfos tools for the create new simulation file. You can click at here. You can save your current files. The number of the files you can save as. At here existing results are present. It is a passive optics module, so calculate for calculation of the reflectance, transmittance and absorption spectra. Absorption modules, drift diffusion modules where we can calculate electric parameters. It is a emission module, it is a scattering modules, master equation modes. It is a shift mode which can multi-variables can be shipped. The both modules, optimization modules, emission zone fit features are also present. The both mode help to extract your parameters and help to find accurate results. It is an example library are given. It is a graphical inputs, script mode. At here the console views and it is a result. It is a geographical inputs where we provide all of the inputs parameters. It is a layer structures. At here the journal tabs and you can see in here graph. Now I am going to create structure of the optical modeling organic solar cell. We can choose at here examples hope absorption and hope maximum photocurrents. But for your better understandings, I will be create my own hope absorption files. You can add more layer through the plus I symbols and provide one by one each layer name. Glass, ITO, P.ps, FT layer, aluminum. It is the extra layer, so you can remove that layer with the help of minus I symbol. Now we need to provide at here thickness value. Top and bottom layer are semi-infinite medium, so thickness are irrelevant at here. For the ITO it will be 130. For the P dot it will be 150 nm, and active layer it will be 160, and according to the thickness you can see at here layer structure will be changed. Now we need to activate at here absorption module. You can ship at here single wavelength and ship wavelength or energy. It will be 300 to 800. It will be 300. It totally depend on you which value you want, but I'm considering at here the same value based on the tutorial. Hope generally investigated that maximum short circuit a function of the active layer thickness as well as investigated the absorbed fraction of light so that corresponding files are reproduced. But for the active layer thickness variation we need to activate SIP mode. At here number of the parameters are given. You can see at here we need to vary only thickness. You can choose at here linear log elements, random log list file. I'm going to select at here the list 20, 40. Now I'm going to provide at here your simulation file name, hope absorption. But for the absorption settings, we need to import at here refractive index files also. So you need to import that here ito.nk. It will be supported .nk file format. At here we will be import spedot.bitron al4071 file. You can import. Now we need to import that here active layer files. For the aluminum it will be al.nk file. For the glass it will be 1.5. Layer structure are completed, absorption settings are completed, chip settings are also completed. Simply click at here the play button. We can see at here our results. It is a photocurrent graph, stacked contribution photocurrent, passive optic properties are given. You can check at here one by one. Absorption, you can change according to the thickness. If you click at here play button, you can see at here the variation. Absorption spectrum for the S polarization and for the P polarization. At here layer absorptions as a function of the with the active layer thickness and wavelength are given. Reflectance, stacked contribution and transmittance. Now we are going to reproduce maximum short circuit current as with the same structures. It is the same layer structures, but we need to change at here active layer thickness variation. In the SIP mode, you can take value at here 10 to 300. Step at here 10. Photocurrent. Simply click at here play button. Now you can see the graph of the photocurrent. You can see at here the variation, stat contribution photocurrent, passive optic properties, layer absorption with respect to the x-axis as thickness. If you click at here you can see variation, reflectance, stat contribution and transmittance. You can see at here the same tutorial which is based on the optical modeling in organic solar cell. As the same graph you can see at here Setfos. If you click like this you can hide these parameters and you can see in that graph log f inverse. Maximum short circuit current are found in here. If you want to compare these parameters, copy all curve of the maximum short circuit current with the comparison of the hope absorption parameter. Simply paste all the curve. You can see like this graph. Now I am going to create fully coupled organic photovoltaic simulation. This tutorial generally based on the Hagerman. According to this Hagerman, if you want to choose the script files, so you can choose solar cell couple exciter and solar cell couple exciton thickness. But now I'm going to create at the same files, and I will be show how we can fully couple organic photovoltaic simulation can be performed in this data. Glass it will be 0, ITO thickness it will be 130, but for the pedot we need to change that value. And for the active layer thickness you can also change 70. I'm considering at here the same data, therefore I'm changing at here some of the value, and otherwise you can perform the same data if you want. We can add here at here surrounding layer, because top and bottom layer are semi-infinite medium, so thickness are irrelevant at here, but aluminum thickness at here 100 nm. For the glass unit will be micrometer. We does not want much calculation of the glass, so we consider at here element 50, because Setfos calculated each nm unit. Refractive index files are already imported in here. I'm going to calculate at here CT exciton parameter, so we need to activate drift fusion setting. Here we can calculate all of the electrical parameters. Pedot in the general tab it will be electrode, and aluminum it will be electrode. In between electrode semiconductor layer must be activated. For the electrode it value 5, and for the aluminum it will be 4.31. At here active layer we can import semiconducting layer at here P3HT PCBA, but in here I will be show if we are not import file, but we can provide at here the data. It totally depend on you which data you want to import at here. 5.3 HOMO value and 3.7 LUMO value. Chargeable site density at here 1 into 10 to the power 29. If you want current parameter, so you need to disable doping and polarity. Optical generation efficiency 0.66. Electron mobility value will be 5 into 10 to the power minus 7, and hole mobility it will be 10 to the power minus 8. We need to add at here exciton parameters, because we are going to calculate CT exciton with respect to IV and thickness. Decay rate at here that value. Generation efficiency 0.66. You can see that here number of the models are given. Most of the parameters are given. Pair separation will be 1.285 for the trap, and it for the mobile sign, and recombination efficiency in here will be 1. If you want to change that here value, you can simply change. It totally depends on you which value you want. For the drift fusion, you can select at here voltage 0.8. We are going to calculate at here exciton parameter. You can change at here step for less calculation. I am going to considering at here voltage for the shift minus 0.5 to 0.8. Step will be 0.1. Layer structure are completed, absorption settings are completed, drift fusion settings are completed, shift settings are completed. Now we need to provide at new name. Solar cell fully coupled photovoltaic. Simply click at here play button. Now we can see at here result, open circuit voltage, short circuit current, fill factor, maximum power density, maximum power density, power conversion efficiency. It is a built-in voltage, current balance, device current you can see it here, exciton density, exciton rate, active layer gains, losses, power conversion efficiency, power density. You can see it here, electrical profiles one by one. numerics, optical integrated photocurrent, state contribution photocurrent, absorption profile you can see it here, energy plus illumination spectral absorption, phase, refractive index, passive optic properties are given in here, absorption, layer absorption are given, reflectance, state contribution and transmittance. For the optical absorption, you can see organic photovoltaic cell consists of multi-layer structure with the layer thickness of the order of the wavelength of incident light, which is shorter than the coherence light of the sunlight. Therefore, OPV is an optically coherent device. This gives rise to interference effect inside, which can be exploited to increase the maximum photocurrent by carefully tuning the thickness of individual layers. At here, active layers considering 70 nm, it can be seen the bottom most of the photon absorbed in the active layer, but also large fraction of photon absorbed by aluminum electrode. To analyze the absorption in aluminum electrode, the fractional absorption each layer and reflectance dependent of the wavelength OPV stack plotted. So now I am going to end here my tutorial. I hope you understand what I want to say in here. If you have any query related to this, you can ask in comment box. In the description box, email are also given. You can email. If you want book or demo, you can visit our website impulsetechnology.in. Who has not seen it my previous video, you can check out the playlist first, second and third my starting video. You can give a lot of the ideas about the Setfos GUI. Thank you very much.